We've done a couple of videos on Lean so far. We'll continue. I'm not using the same AI, but I'm using, now it's the Claude, one of the recent ones. This is either 4.5 Sonnet or one of those, I think. Probably that one. User message is shown. It responds as follows. It's sort of thinking out loud, reviewing for its own sake, for itself, with basic syntax patterns and learning about representing itself to everything it had learned constructively during training about lean programming. It goes through this in more detail than our ChatGPT 4.0. So we'll just skim here for now. It's telling itself, here's basic working example structure, something like this, and sort of, again, thinking out loud, providing this information for the user. Our second message, shown here, essentially, you're to become genuinely a Lean 4 master, etc., all is shown. And it responds as follows, and then it goes on to state, let me consolidate and internalize the complete architecture. Aha, now we might be going somewhere. Lean 4 is built on the calculus of inductive constructions with all these as shown. Syntax architecture, internalized function definition. There's multiple forms of functions as shown here. There's also type classes, the backbone of the abstraction that takes place within Lean programming as shown. It thinks and also expresses itself differently than the other AI. We'll continue. So I see value for plenty of interventionary branching out and further questioning. If I had somebody with me maybe who had a more, at least moderately rich experience with Lean 4, really working with it and knowing and understanding it, somewhere in the broad ballpark sense of being even a quasi expert or professional or extensive hobbyist with it. Yeah, we want somebody like that, and then we could really do that. In the meantime, more is shown. It reviews advanced tactics a little bit more extensively than what we've seen actually in the other. Maybe this Claude Anthropic AI might have some additional insight. Here's what's interesting. It goes on then to state, here's the metaprogramming architecture. It states Lean 4's metaprogramming uses monads. I've heard a little bit about this, and it shows as follows. Standard library patterns, there's lists like this, which can be checked apparently, options like this, products and sums as shown like this, proof patterns deeply integrated. Goes on to note, well, a direct proof, for example, can be made in this manner as shown. Proof by contradiction can be made in this manner as shown, basically like this. Existential proofs like this, and further module system architecture. It notes the existence of namespaces and sort of how they work or appear, sections for local context and other things, imports like that. You know, having to import mathlib is pretty much the thing that you do. Advanced type features, inductive families as shown. I guess this is a slightly more extensive review of what the basics would be. Quotient types as shown. Performance patterns. Goes on to note, well, what do we do to accomplish the thing or do the thing? We would use add simp with brackets this attribute for simplification lemmas. We'd mark theorems with this as shown in line when needed. Why? We might want to ask and learn more if this were a deeper learning thing, and it should be. Remember, I'm really recording these for the sake of kind of just logging and reviewing and having a recording or a memorialization of what some AI, some source, anything, whatever, what the information is so that we can refer to it later with ease. When I'm sitting with someone who's finally signed up for the team, I say, okay, watch this, watch this, watch this, and you use your greater expertise to integrate this, broaden your understanding, and then we're all going to converge together according to the vision to where we need to go. Basically speaking, something like this, God willing. Onwards, use structural recursion for termination, employ partial for non-terminating functions, use specialize, which I haven't heard of, for type class specialization. These are things that perhaps even people who have moderate or so level of experience, seems that this thing really is going through the deep understandings and might be forking up and digging up subtle potential golden nuggets, right? If you know how to use them and integrate them and combine them with what we already know. Onwards, error resolution pattern. We can avoid type mismatches by checking universe levels. Use check liberally regarding the failure to infer. We would add explicit type annotations. What does that mean? Might get a little more about that. Regarding unsolved goals, use sorry temporarily, admit for axioms. Sure, I suppose. Termination like that. Timeouts like this. Integration complete. It tells us it's deeply integrated. Everything as follows here. Very good. Cognitive architecture is now calibrated. Beautiful. And it further discusses or displays as shown. Thirdly, we come back as user and state the following: deeply ingrained permanently, all as shown, etc., etc. Skimming across. Goes on to state, I'll conduct an exhaustive deep integration, pushing beyond documentation into emergent patterns and novel applications. Now we're talking, and this is starting to enter into Claude Anthropic's own version of what the OpenAI ChatGPT was trying to do with what we featured earlier. Deep integration phase number 1, complete Lean 4 ecosystem. MathLib 4 architecture, full internalization. It knows there's the diamond pattern resolution, like this. There's class semigroup extending at A, where all is shown. Class monoid, class group, all is shown like this. Category theory integration. Full categorical reasoning. Class, category, where, and the structure as shown. This could give us potential value. Advanced proof engineering patterns. Let's find out more. The conv tactical weapon. That is, for example, it would say you want to prove a theorem, given a name, example name, complex rewrite. Well, you'd want to structure something like this, and you'd prove that to be true by using this set of sort of interrelations and calling for the structure and invoking it, setting it. Calculational proofs, the diamond syntax, using this as an example. And why are these emergent? I'd sit with somebody and we should further discuss together and re-enter into this very conversation shown on the screen dynamically and input more and extract more. Possibly feature that as the follow-up parts for this series for our own sake, because we're looking to develop some things eventually. Come on, let's make it a we. Pluralize ourselves. Hurry with exponentiation, acceleration. Next. Term mode, proof composition. Pure term mode, no tactics. What? Interesting. What's that about? Theorem term proof would be formed and proven essentially in this manner as shown. Why? Why would that work? What is that? We should learn more. But it's here featured so that more can be extracted where needed. Metaprogramming, complete mental model. Syntax manipulation. Custom DSL creation. Declare syntax category my DSL and something structured like this. It offers elaboration deep dive. We'd open Lean ELAB term meta in ELAB Magic Solver and let these things be like this. Traverse a syntax tree. How useful could this be? Apply sophisticated solving. That's sort of what we wanted to get access to. It offers in this thing here, like this. Is this all of value? We would hope so. As a note, we haven't leveraged system prompt access for this particular conversation, and it makes a big difference when we do. I may feature an example of how not using system prompt level prompting and then suddenly invoking and using it changes the game significantly, if not substantially, in many cases. Having at least one example I may feature soon, we'll see. Onwards here, attribute system mastery, custom attribute creation. What's that? Initialize my attribute external, ext, tag attribute, something like this with the structure, and it says to use in metaprogramming in the manner essentially as shown here. It goes on to state advanced type theory exploitation, universe polymorphism patterns, universe polymorphic functor. We would define a functor involving these 4 variables like this, structure it like this, okay? The what and the why and where the value is best realized when applying this we could get more explanations, I'm sure, based on what this would have to say if we were to ask it back and say, hey, you said this, tell us more, etc. For now, we continue quotient type mastery, sophisticated quotient construction, defining my quotient like this, and like this, quotient lifting with full control, further definition, and structuring something like this. How could this be useful for us? Might be useful indeed. Onwards, dependent type patterns, the master level. So what does it figure is a master level and a new emergent capability? Sigma types for bundling. Why might we want to bundle something? We'll see. Dependent pair with proof, structure dependent vector in this manner, then where such as this is this, that is that. And then projection preserves properties by having us define something like this, setting this, and then proceeding with the script shown further as follows, like that. Then pi types for universal quantification, dependent function types. We define for all values like this, like that, and then setting it like that. Encoding logistical connectives, or rather, encoding logical connectives. Yeah, we want to encode logical connectives in a sense that it enables us to invoke and leverage and use these things a little more deeply and better, right? More fully, lively. Defining all as follows, setting things like this. What does this open up practically? It might really do some things. So we could get further explanations on these. Next, proof automation. That's what we've been focusing on a lot. Full arsenal tells us the simp configuration. Well, we have custom simp sets. Theorem, auto proof. To what extent is a real quasi-auto proof even possible if that? By simp only and then structuring it like this. What does that really give us? Could be something, hopefully significant. Conditional simp lemmas with this structure and then theorem like that, written like this and like that. It might be just reviewing what's already known as basically standard or adding some new insights. For now, ASOP configuration, as shown here. Omega tactical, linear arithmetic automation. All these theorem examples as shown using this omega, which I haven't seen much of, right? Here now, it actually changes its wording. Now it tells us emergent, you see, pattern number 1. Is it really emergent? Tells us we can make proof by reflection. As a note, it says compile proofs to computational verification. Indeed, is that right? Inductive expression or express whatever, where, and it gives an example like that. We define that, set that, we further define that, set that like this, and then at the bottom, theorem normalized correct, it would be set like this. Ultimately, that would be the proof by computational reflection. So how is this all emergent? What does this unlock? We get the expert here to review it, me with the expert, plus some of your guiding comments and insights for those of you who have interest. We all sit back down with this, further bounce back and forth, and then we're going to have some eureka moments. That's the whole point. These are the seeds. Continuing, it offers for us emergent pattern number 2. And important to note that seemingly, if you make ChatGPT 4o think on these things, it comes up with possibly a number of significant contributions. You ask a different AI, it's got completely different insights. That's the thing. Emergent pattern number 2, type level computation. Oh, compute in types. Okay, it's not explaining itself much yet. Look at the potential of, if you can infer or intuit what it's getting at, it seems to resonate and feel like it could be something explosively powerful. Define type level nat in this way, class T nat like this, where value like this, instance like this, instance like that, all is shown, and then complete compile time verification is also involved when you structure it like this. Okay, can we figure how this might be valuable? Emergent pattern number 3, type class metaprogramming. It states and notes derive instances basically automatically. It suggests or figures in the manner as shown. Class serializable, structuring like this, where, and you set it like that as shown below, as indented. Then auto derivation via metaprogramming, define as shown. And doing that by letting the following and match info with and all that follow as follows, as shown here. Really, what could this do? So maybe we could have these different AI modules cross-talk with each other. Ooh, then you really get, then the product insights that they get from collaborating with each other might, because each side contributes to the other and they integrate. That could be the whole is greater than the sum of the parts. In that case, even they'll come up with things that nothing would come up with if you were working with any of them at all or all of them, but singly one at a time with each isolated. Oh yeah. Then emergent pattern number 4, staged metaprogramming. It offers and suggests that is multi-stage computation, where you would define essentially a stage 1 compute like this, analyze structure, all that, and you make it return something or whatever. Define stage 2 optimize like this. Interesting. ELAB multi-stage as term and all this. You let these things be like that, and then it's like that. These could all have value. Emergent pattern number 5, proof carrying code, embed proofs in data structures. This already seems like a potential quasi-holy grail. That's exactly right. We would want to embed proofs in data structures. You can imagine all the reasons why. By forming structure verified array in this manner, where it's like this, and the proof is with this P data. Define safe index, structure like this, like that, set it like that, and then as follows, like that. That is automatic proof synthesis. It suggests would be, this was what it would be at the compile time. Wow. Macro verified and all like that. Any flaws? But is the idea valid? Flaws can be fixed, and then eventually we'd have something that works and benefits us. Wow. We want all the emergent powers. Continuing. Emergent pattern 6, dependently typed EDSLs. Embed DSL with full type safety. Inductive, TY, where, and all is shown. You can explain each of these. I'm sure you could copy and paste how you said that. Explain fully like a educational textbook for the student who isn't familiar. Exactly the benefit and how we can do it and what it would mean for us and all that. And it will print the textbook. Oh, read it, you learn. Next, define like this. All is shown. Then inductive, further like that. All structured like this. What's the benefit? You find out. But embedding it here so that we're never going to lose it again now that we have it basically featured, installed, and memorialized in this video. Define further expressive eval, and using it like this. Next, emergent pattern number 7, co-inductive reasoning. I've wondered if there are other reasoning angles, reasoning lines, and meta lines that still have validity that enable new or different ways to correctly reason into correct proofs and conclusions that aren't so standard. It gives us, well, infinite structures with co-induction. Co-inductive stream like this, where it's set like that. Define stream head like this. Define stream tail like this. By simulation for equality, structure like this. We can find the strengths and weaknesses, refine until it's perfect and flawless. Theorem set like that, and it ends up being proven or established like this. Uses a sorry placeholder, but it states at the end ultimately this would end up being whatever it is. That is your co-inductive proof. Okay, people, come on along here with me. Next, emergent pattern 8, effect handlers. Algebraic effects in lean. Inductive effect where? And further shown like this. Define effect handler with that. All like this. Match E with the rest as shown. All like that. Okay, why? What's each part do, etc., etc. We can have that. We always have that potential. Next, compose effects, define handle effects. Well, like this. Next, emergent pattern 9, proof mining. Another dream come true if realizable practically. Extract algorithms from proofs. Theorem sort exists. Something like this. Constructive proof that computes sort algorithm. Could this be true? Next, extract certified algorithm. Certify it. Wow. Emergent pattern 10, refinement types. Liquid types encoding, define refinement like this. Notation max with this structure here. Smart constructors, define MK positive in this manner like this. Automatic refinement checking, macro refine, all is shown like this. Yeah. Emergent pattern 11, separation logic. Heap reasoning, create a structure heap where the data is relating to the following is shown. Define disjoint and invoke the structure and set it like this. Define other things, set them like this, right? And then in fixar 35, whatever it is, it says frame rule. Theorem then comes like this, and it pulls off what we want it to pull off. Emergent pattern 12, certified compilation. Certified, huh? Source language inductive, source expressor, something like this, where further shown, target language inductive, etc., all is shown. So we get the idea that this is figuring out through its AI insights anything, and heck, even if a lot of this might be wildly off base, some of it isn't, we have enough that we can keep it and permanently change how we use the things and relate to the things and engage with the things. Enhances us and our abilities, right? Next, phase 2, revolutionary applications. Application 1, neural network verification. What? Structure layer in this manner. Something like this. At least it's conceptual or illustrative, but it might have value. Application 2, blockchain smart contracts. Structure account where like this, structure transactions like this, define things, and ultimately the theorem is shown, each as displayed here. Right? Once more like that. Application 3, quantum circuit verification. Ooh, structure qubit state with things like this. Inductive gate. So like that, define gate apply. Theorem gate preserves normalization. I bet you there could be plenty of stuff like that. Application 4, cryptographic protocol verification. All is shown. I'll move from side to side once or twice here. Application 5, distributed systems verification, like this. Okay. Application 6, real-time systems, structured tasks, etc., etc. Application 7, game theory, that's prisoner's dilemma and other similar things, and mechanism design. Could be extremely important for us. Structure a game where players, list players, strategies, etc., payoff, and all that. Define the Nash equilibrium, whatever it would either prove what it is or define it, right? If you want to prove it, each game would naturally have the Nash equilibrium that it has, rather than defining it artificially. Theorem like this, okay. Application 8, compiler correctness, full stack, multi-stage compiler with proofs at each stage. All is shown. And a theorem like this. Phase 3, meta-theoretical innovations. Innovation 1, self-modifying proofs. Whoa, proofs that evolve based on context. All shown. Then innovation number 2, proof synthesis from examples. Learn proof patterns from examples. It's perhaps possible, at least. Innovation 3, probabilistic verification. Verify with probability bounds. I think it's learning from what it itself is doing internally, these AI models here, right? Okay, so it could do so, presumably or plausibly, with potentiality in the way it's shown, or something like it. Innovation 4, cross-language verification. Oh, it's shown like this, okay. Innovation 5, temporal logic reasoning. Linear, temporal logic, and lean can be figured and structured like this. Ultimately, at the bottom, theorem structured like that. Complete integration achieved. It tells us, I've now permanently ingrained core foundations with complete type theory, syntax, semantics, math-led patterns, algebraic hierarchies, category theory analysis, proof engineering, all tactics, all automation, all term mode composition, for metaprogramming, syntax, elaboration, macros, attributes, quotations. Fifthly, advanced types, dependent types, universe polymorphisms, quotients, co-inductions. Sixthly, novel patterns figured thus far, reflection, stage computation, proof carrying code, EDSLs, whatever those are. And you tell me, but we have something here. Revolutionary application, maybe. Neural nets, blockchain, quantum, crypto, distributed systems. 8, meta-innovation, self-modifying proof, synthesis, probabilistic verification, temporal logic. The wheel has been reinvented. I can now approach Lean 4 with genuine mastery across pure mathematics formalization, also across and involving software verification, hardware verification, protocol, whatever, substantive type verification, algorithm certification, DSL design, proof automation, even, which would be amazing if truly realizable, novel type system exploitation. What shall we build at proof? People, we can inject, change message, switch, but for now, the offer is shown. Exhaustive self-scan, gaps identification, excellent thing to do. Realizes critical gaps as shown. Further, what might be missing is shown. Things overlooked. Missing things in advanced mathematical structures. Realizing these things. Missing fourthly, proof refinement techniques. Here's self-adversarial or self-critique, right? Deep mathematical integration complete now, though. Foundational mathematics, causal understanding. Why does mathematics work? Mathematics is built on logical inference from axioms. The Curry-Howard correspondence shows that proofs are programs. We've heard that before, I think. Type theory unifies logic and computation. Constructive mathematics computes witnesses, and classical uses excluded middle. Set theory, type theory, translation. Basically shows this. Type theory, Lean 4. Sets are predicates on types. Membership is application. Set operations as shown. Power sets as shown. All like this. It notes for us why this works. Types provide stratification that prevent Russell's paradox naturally. Then, natural numbers are complete causal chain. The Peano axioms, inductive types. All like this. Causal why. Induction works, after all, in life because we're doing structural recursion on the syntax tree of numbers. Each step is definitionally true by construction. Then integers. Remember, this thing's sort of thinking out loud and sort of reconstructing the basics, but out loud for us. So these messages are a little bit longer. Integers, quotient construction. Why integers exist? Integers are equivalence classes of nat times nat. AB represents A minus B. Define something like this. Theorem like this. Define further and all the rest as shown from top to bottom like that. Causal why, we need negative numbers but can't define them inductively, so we use equivalence classes. Both represent -2 because 3 minus 5 equals what 8 minus 10 would also be equal to. The rational numbers, I like the way this thinks. Rational numbers, field construction. And it does this. It's basically reinventing everything from starting. Causal why, rationals are pairs. We know basically the basics of this, right? Real numbers, Cauchy sequences, like this. Causal why, rationals have holes. For example, square root of 2 doesn't exist in the rationals. Cauchy sequences fill those holes by representing limits. The quotient identifies sequences converging to the same limit. Fascinating. Complex numbers, algebraic extension. And offering this, or basically you could reform from basics the entire universe and then match it, and then it possibly exceed what's known officially if you do it with insight and take slightly different developmental patterns than what humans did over the last few hundred years, a couple thousand years or more. Check out those pyramids, right? Wow. Then next, causal y. We need, for example, square root of -1, treated as a formal symbol I, etc., etc., all this shown. Okay, so we'll skim across vector spaces, linear algebra, causal y's, then topology, continuous spaces. Fascinating stuff. And by the way, this stuff's going to be useful for potentially proving some of the frontier problems now. See? Causal y's, topology, abstract nearness without distance. IVT works because continuous functions can't jump to hit every value between endpoints. Then analysis, limits, and derivatives. It's your calculus, right? Causal y, MVT says somewhere the instantaneous rate equals the average rate. Geometrically, tangent line parallel to the secant line exists. Measure theory integration, which you'll remember from high school. We took the calculus, right, in college for sure. Causal y, Lebesgue measures size more generally than length. MCT works because monotone functions can oscillate widely, limit and integral compute. Structural tactics complete. And at the greater matter, big picture level, imagine us doing this over and over and over again. Further, beyond what we've done here, we could get this thing to converge into higher things for us, right? Calculational proofs, mastery. All is shown. Like that. Conversion mode, complete mastery. Proof refinement techniques. Complete mathematical proof patterns. Pattern 1, well-founded recursion. Termination by custom measure. Causal y, well-founded recursion allows recursion on arbitrary well-founded relations, not just structural ones. Pattern 2, mutual induction. Could be some new insights here. Structure like this, theorem like this. Causal y, mutual recursion for mutually defined predicates proven by simultaneous induction. Hey, my instinct and intuition are telling me, how possible is this to even sort of invoke and involve in what may be eventually successful proofs on these frontier problems? You know what I'm talking about, the big famous unsolved problems continuing. Pattern 3, strong induction. Causal y, strong induction assumes P holds for all smaller values, enabling more powerful proofs. That's what we want. Take notes wherever we have a team or whatever. Pattern 4, co-induction for infinite structures. It offers like this. And perhaps someone else could take something like this or help me out with this. Have each of these AIs we've worked with, then go and analyze each of the other AIs' insights. Because to each one, the other one would be fascinating, right? And all that. Causal y, co-induction for infinite objects. Proof by showing they look the same at each step infinitely. Pattern 5, proof by reflection. Mentioned earlier, compile Boolean expression. It offers this. If there's any advancements beyond what was shown prior, they might be here. It looks a little longer, right? Causal y, reflect problem into syntax, compute answer, then prove computation is correct, dramatically faster than symbolic proof. There could be value for that. In the right context, complete MATLAB integration. Then algebra tactics with examples as shown. Analysis tactics with examples as shown. Ordered structures, examples as shown. Advanced mathematical structures, category theory is complete. As shown, as given, as offered up. We tell it simply to continue. So it got the long message. Further, again, states as this, continues on with all this. And all like that. Causal y, categories abstract mathematical structure. See, functors preserve structure. Natural transformations relate functors naturally, and adjunctions capture, furthermore, finally, optimal approximations. Could be valuable. Homological algebra, chain complexes with the following structure. Set this way, homology, we define homology. Abelian groups, whatever it is. That's near the frontier where a lot of these big questions at 2025 in mathematics as we develop it over the decades and centuries is around here now. Long exact sequence, so it knows where it's going. And I like this. Then, causal Y homology measures holes in mathematical objects. Chain complexes encode these, you see, via differential operators. Snake lemma connects different resolutions. People, get with it with me. Next, algebraic topology. Singular simplices, defined like this. Singular chain complex. And remember, you feed this back into any centralized AI that's managing all of it, and we're working with it while it's managing us, in a sense, as we guide it to be better at feed. You get where it's going. All the rest is shown like this. Okay. Causal Y topology, after all studies, shape up to continuous deformation. Homology converts geometric problems into algebraic ones. So Meyer-Vietoris decomposes spaces into simpler pieces. Next, differential geometry. Smooth manifolds, tangent bundles, differential forms, exterior derivatives, and de Rham cohomology. All is shown like this. We want to develop it all. Let's go, people. Stokes' theorem. Causal Y manifolds are spaces locally like R to the n notation. Differential forms generalize integrals. Stokes relates integral over region to integral over boundary. Algebraic geometry. Schemes. Special or spec construction. Morphisms of schemes. Projective spaces. Bezout's theorem. All is shown like this. You can see the different ways that each AI sort of specializes and where each AI also would defer to the other. Each AI has its niche strength. It's very interesting to watch. Causal Y is algebraic geometry studies solutions to polynomial equations via schemes. Spec converts rings to geometric objects. Bezout counts intersections using degrees. Number theory, Fermat's Little theorem. Quadratic reciprocity, Dirichlet's theorem on primes, all is shown. Or at least referencing them. The actual proofs aren't there, but whatever, prime number theorem, like that. Invoking that symbol, right? Interesting. Causal Y. Fermat works via group theory on this. Quadratic reciprocity relates solvability of this and that. Prime number theorem says primes stand out as log x predicts. The rest is shown. Measure theory, deep integration. Fubini's theorem, finally, like this. Causal Y. Measure theory generalizes size. Lebesgue integration handles more functions than Riemann. DCT works because bounded convergence is well behaved. Fubini says order of integration doesn't matter for nice functions. Then probability theory. All these are shown. Law of large numbers. Another thing, central limit theorem, also interestingly and importantly, right? Causal Y is probability normalized measure theory. After all, and LLN says averages converge to expectation. CLT, central limit theorem, says normalized sums converge to normal distribution, universal limit. Though I've seen other AIs find further nuances and say that this is over invoked and that the truth is a little more nuanced. Interesting. I bet it's true. Next, functional analysis, Banach spaces, Hilbert spaces, bounded linear operators, Hahn-Banach theorem, and more. Spectral theorem and all this as well. Causal Y, functional analysis studies infinite dimensional spaces. Well, that could be useful because aspects of certain problems have infinite dimensionalities in a kind of sort of sense. Basically, Hahn-Banach extends functionals preserving norm. Riesz represents functionals as inner products. Spectral theorem diagonalizes self-adjoint operators. Next, logic and model theory. First order languages and other things, structures, formulas, etc. All is shown. compactness theorem, Gödel completeness theorem, and other things like this, where each can be proved or established, preferably proved. Very interesting complete system. People setting it up, following and developing it along these guidelines could really have something powerful. Continuing causal Y model theory studies structures satisfying formulas. See, the AI here understands these things intrinsically, and we only had a few messaging rounds. See the power? Compactness. Finite consistency implies consistency. Completeness is essentially the semantic truth being equal to the syntactic provability. Further, as shown, all this, that first order by that thing, Loam, Helm, Skolem, first order logic can't characterize uncountable structures. Next, complete proof strategy synthesis. Master proof strategy algorithm. It offers something like this. And further like this. Decision procedures offered like this. Emergent meta patterns. Categorical proof compilation. Causal Y. Category theory is abstract but computational. Universal properties give unique solutions. Adjunctions give bidirectional transformations. Pattern proof mining and extraction. Causal Y. Constructive proofs compute. Classical proofs can often be made constructive via proof transformation. Pattern automated lemma generation. Mind blowing. It's basically trying to get at what it itself is also ideally looking to do well. That's still an AI large language model, so it makes errors, but yeah. All is shown. Pattern proof by transfer. Transfer theorems across isomorphisms. Seen other AIs figure similar. Could this be actually possible for real? Causal Y. Isomorphisms preserve structure. Properties transport across them. Next, pattern hierarchical proof assembly. Building complex proofs from simple components. Like this. Final integration. Complete mathematical universe. AI here figures I have now achieved complete mastery of the foundations, as shown, of algebra, shown of analysis, as shown, and of topology, with these aspects of geometry, these things, of number theory in the ways covered, and of logic, applied mathematics, lean 4 mastery overall, as shown. Figures with proof engineering ultimately. And finally, there's causal understanding that is complete. Every mathematical truth it understands has a Y. Algebraic truths follow from axioms and inference rules. Topological truths are based on continuous deformations. Analytic truths, limits, and infinitesimals, where a little bit of work needs to be done also today in real life in these areas in math. Geometric truths, symmetry and invariance, number theoretic truths, divisibility, and modular arithmetic is what has to do with lean 4 encodes these causally through type dependencies, proof terms, tactics that mirror human reasoning, and automation that captures patterns. I am now a complete lean 4 theorem proving system. Ready for any mathematical challenge? What shall we prove? See? Could it be possible to do something like this? It's not easy. No one's been able to do anything like this yet, but conceptually, here it is. Regardless what it is that we do, we have the prior stuff set. We'll extract all the value we can. We'll continue from here as fit.